Good afternoon, everyone. Thanks for joining. This webinar will begin in about 2 minutes. Hello, everyone. Thank you for joining this webinar. Bonjour tout le monde. I would welcome you to a community consultation about heterogeneous integration. I'm Andrew Fung at CMC Microsystems. I will be moderating the discussion today. I would like to begin with an introduction to CMC Microsystems for any who are joining who are new or unfamiliar with the organization and the National Design Network that CMC manages. Three segments will follow then in the remainder of this webinar. First, we'll hear from Professor Amr Helmi at University of Toronto with a perspective on heterogeneous integration roadmap. And then from Gordon Harling from CMC Microsystems on one specific solution under development involving a silicon interposer platform. We'll conclude the webinar with a time of discussion and feedback from all of the participants about your experiences and your needs in integration, aiming to gain some understanding on what solutions are needed and hopefully spark off some, plant some seeds, I suppose, for further collaboration in the near future. Let me begin by introducing CMC Microsystems and what we do in Canada and in the world. CMC is a not-for-profit founded in 1984 with a mission to provide essential services in the microsystems and nanotechnology space for technology developers in Canada and beyond. This will touch on technologies of the future, such as Industry 4.0 and the Internet of Things and 5G communications. In doing all of this, we wish to lower the barriers to technology adoption by offering services and products in three main areas: CAD, Fab, and Lab. In the CAD area, CMC distributes through a network access to industry standard design tools and accompanying process design kits that tie into fabrication technologies. The middle panel represents fabrication technologies at a variety of technologies in microelectronics, MEMS, photonics, and some emerging processes. And the right panel, lab, represents services offered for testing, custom R&D, contract services, and proving out a prototype that results from the previous two panels. So while the manufacturing of various types of technology can proceed decoupled, such as an electronic ASIC or a MEMS gyroscope, photonics, or other process, we understand that these technologies need to have a ready solution for integration into a functional module that's testable by the prototyper. And so the aim of this consultation webinar is to present a roadmap view with a few perspectives on specific solutions for heterogeneous technologies. So with that, I would like to hand over the presentation to Professor Amr Helmy at the University of Toronto. He's a member of the IEEE Heterogeneous Integration Roadmap Committee, where he serves as the co-chair of the Technical Working Group for Integrated Photonics. So I'll hand the screen share over to you, Professor Helmy.
Thank you kindly, Andrew. I appreciate it. So welcome everybody. Can I just confirm that everybody can see my slides okay? Perhaps you can confirm that, Andrew?
I don't, I see black screen.
Maybe it takes some time to load up. So.
So in the share button at the bottom of your screen in the control bar, I think you can select what window you want to share, or you can share your entire desktop. Could you just verify you have shared the presentation?
Yeah. So let me share. How's that?
I still don't see anything.
So when you connect with the share button, you should see several boxes. And once you go on it, you either double click or hit the screen share at the end of it. I can't pass it to you.
I mean, I have, yeah, this is what I have, and I have a.
It was up working earlier.
I'll stop sharing and I'll try again. Share. I am choosing to share the desktop.
Just flashed up.
Okay. And I now have my PowerPoint on the desktop. And it's still black?
Yeah, it's still black. As a backup, would you try emailing your slide deck latest version to me, and I can try to cast it from here?
Yeah, sure. Okay, how's that? Can you see anything? Is there anything coming on the screen, Andrew?
No, not yet. Sorry, Art.
So if he emails them and you present them, it's probably going to work best.
Yeah, it's just going to take a while until I send this to you, so it's a bit of a shame, but here it is.
Sorry about this delay, everyone. Will just be a moment.
Yeah, it should be in your mailbox now, Andrew.
Okay, just waiting for it to come in.
Start with everyone.
Could I start with the deck that you'd sent me earlier?
No, it's not the same one. So I'll stop sharing now, assuming that you should have the one, or you can, yeah.
Might be the file size.
Okay, it's in my inbox.
Okay.
Great.
In the PDF, you can go back to the Zoom.
It's right here.
Okay, you're on screen, so hit share.
Just the full thing.
Or wait, what did you want to show? You wanted to show what's a PDF?
Oh, come on. This, right? But it won't, I don't have anything else to open the PDF. Okay.
Well, you can just share your screen and just make sure you don't put anything else up.
Okay, here we go. Okay, can everyone see this?
You on mute?
Yeah.
I can see it.
Yes, I can see that.
Okay, sorry about that delay. Go ahead.
Sorry about that, everybody. So this worked the first time. We tried it 15 minutes before the meeting, but it didn't work during the meeting. Sorry about that. My name is Amr Helmi. I'm a faculty member at the University of Toronto. My research involves photonics and photonics integration and devices. However, I also have some activities in the road mapping within IEEE. So I'll talk to you about the effort related to heterogeneous integration, and then I'll speak about slightly more topics that slightly more represent the electronics and photonics communities within Canada. So if we go to the next slide, the heterogeneous integration, basically, I'll give you an overview in 10 minutes, and then I'll use another 10 minutes to speak to you about some of the things that are more specific to Canada. So don't be intimidated by the 58 slides over there. I'll speak to you about overview of the landscape where this HIR started, which is basically post ITRS. I'll speak to you about the heterogeneous integration, the path forward through this road mapping activity, and I'll speak about a few examples related to performance enhancement based focus rather than transistor count and integration density based focus, as has been the case with ITRS and ITRS 2.0. I can go to the next slide, please. I wanted to highlight that this activity is organized through IEEE, but it's also extremely international. About 60% of the participants of this effort are actually from industry. It's a pre-competitive, but IEEE, as you can see from the sponsors down in that slide, along with the FOTSOC SEMI, which is the sort of the world's largest supply chain in the semiconductor field entity, if you will, also the Packaging Society, Mechanical Engineering, ASCME, and the Electron Devices. So it's truly sort of international and multidisciplinary effort as well. If we go to the next slide, please. So as a preamble, Moore's Law has changed quite a bit. It has evolved quite a bit. There is a level of saturation that is undoubtedly you will see. And if you don't, I will help you see where life has evolved beyond us trying to just simply increase the number of transistors on a chip through miniaturization. So there is a period we're entering now where some of the sort of the pace of innovation, the requirements, and the need, sort of the meeting the demands through just sheer integration is actually costing us more. So as you increase the number of transistors on the chip as we see it right now, you're actually getting a cost with less performance. So something else and a slightly different focus needs to be done to mitigate this limitation. Next slide, please. So here's one example of that. If you see at this point in time, as time in the x-axis goes up, the number of megabytes in the DRAM now has been slowing in its pace as a function of time. The different slopes where there is a 2x, or 1.5x, 1.4x is coming now to 1.1x every sort of 2 years. So now you need 7 years to actually reach a 2 times enhancement. If you go to the next slide, even more evident, you will find that basically the performance of an actual computing unit when it compares to the VAX, which is admittedly, it is archaic, but at the same time, it serves as a useful benchmark, has been not only saturating, if you look at the last 2 points, it's been going down. So if there is nothing you can do, or if there is nothing you're doing about these sort of processing units in computing, and you are just simply packing up density, you're actually losing out because of IO and thermal and power considerations. So this is clearly not a state that could go forward from an electronics standpoint. If you can go down one more, please. So another technological, if you like, or even socioeconomic consideration is the sort of the landscape that existed sort of in 06 versus 18. If you look in 06, if you had all invested in sort of oil, and the banks would have done really great. At this point in time, most of the growth is happening in data. So if you look at the biggest 10 companies or the biggest, largest companies by cap, you'll find them predominantly sort of IT. Next slide, please. So this is a huge growth market. So the structure of the economy, I guess the gist of it is change. Next slide, please. So how and why did that happen? Initially, that was the road mapping started with the NTIS, which started in the United States. After that, it actually became more encompassing and became significantly more international to lead to ITRS as we all know it. ITRS evolved and followed Moore's law very faithfully, almost fulfilled it, you could argue, to ITRS 2.0. But the last report on ITRS 2.0 came out in July 2016, and there was no more. The focus of ITRS that is different than the focus of HIR, if you will, is that it actually was focusing on the integration density, and there was an implicit assumption that the integration density went hand in hand with the performance. As I've shown you in the last few slides, that is no longer the case given the state of the technology. The next slide, please. So HIR started and basically started with these societies, and it focuses on doubling the performance through heterogeneous integration by getting the best of different technologies and putting them in a hybrid fashion together. So the focus and the difference in the focus is not on any integration density per se, but the power of integration to increase the performance of a given function by manyfold. Next slide, please. So that's exactly what I just said. So we can move to the next slide. And next slide. So that's also what I said in the words. Can we move to the next slide, please? So basically the definition of heterogeneous integration for us who are not familiar is that we get parts made in different foundries. In this particular example, it's actually a silicon in a package, which is a sort of a relatively well-developed technology, and we, in a heterogeneous fashion, integrate them in a functional fashion with irrespective of their component type, circuit type, or bonding type. And when we do, given the power of the interconnection itself, we can achieve the circuit on the right, which is called system in a package, and it allows us to have performance much, much larger than the sum of the individual parts if they were put separately. Next slide, please. This is a definition of heterogeneous if we're going to go for those of us who are not familiar. The next slide. So the key is to go through separately manufactured components to put together. Here are examples of the power of that. So without heterogeneous integration, we would not have smartphones with the power that we have. So the next slide is a reverse engineered iPhone 8. And if you look at the assembly, many of the chips, number 11, number 2, number 17 and 18 are actually stackable dies. They're basically a fan out system in a package and another system in a package, high bandwidth 10 nanometer DRAM memory. And this uses a 10 nanometer node. Without these 1 to 22 bits that are all heterogeneously integrated, you cannot get the power in the phone that you're either using to listen to this call or just sitting next to you. So just this tells you that heterogeneous integration is not something pie in the sky. It exists. What we're trying to do is to put it in a roadmap and utilize it much better, not just from an electronic standpoint right now, because all these 22 chips are actually stackable, heterogeneously integrated ones in iPhone 8, which I'm holding in my hand right now, actually. But we would like to take this beyond to MEMS, to photonics, to many others, so we can enable the advance in functionality that is brought to this electronics industry through heterogeneous integration to also other domains. Can we go down for a slide, please? So high performance computing applications, if we go down one, you'll find this is the sort of, in not most recent, but one of the most recent 2.5D heterogeneous integrated AMD engines. So the GPU itself is heterogeneously integrated with the high bandwidth memory. So you can get the exchange rate to be at basically a terabit per second. Otherwise, you'd never be able to have that data rate. So the GPU itself performs only as a function of how fast you can get the data between the GPU and the HBM. So the HBM, the high bandwidth memory, that run at 900 gigabit per second in that. There are now sort of aims to go beyond 1 terabit per second. But at the same time, that would not be possible without heterogeneous integration. If you go down some more, I think this is what I would like to say about sort of basically heterogeneous integration. I'm going to keep going down if you don't mind. So we can speak about, yeah, this is Intel, the EMIB, the multi-die interconnect bridge, where Intel basically has some sort of a interposer where it can take a 10 nanometer node, an AMD GPU. I mean, we would have never thought that the recent products that are coming out this year from Intel actually are using an AMD GPU. And this could only be possible through heterogeneous integration. This is a real product. And the only way they could do this is they can port the designs, the schematics of the AMD prior to build the heterogeneous interposer, and they can build it later and put it together later. This is just an example of the power of individually manufactured parts that can actually enable new performance metrics that were previously untenable. Next slide, please. So we can go down some more, can do some more. So there are lots of applications where this is where the roadmap is addressing, and many of them are cross-cutting. So we're looking into the test. How do you test all these things? How do you address heterogeneous integration in IoT, medical, health, wearables, aerospace and defense, integrated photonics, MEMS, 5G. 5G is a huge application as well. How do you co-design that stuff? What's happening with security? How about thermal management, which goes across every single topic? Supply chain, that's why SEMI is on board. Lots and lots of technical, but also logistical aspects that the roadmap is involved in. Next slide, please. So lots of events around. If you'd like to get involved, let me know. We're looking for relevant volunteers from industry and academia. Keep going, thank you. So there is a global advisory sort of council, keep going. There's a bunch of individuals who look at it from different, or try to shepherd it from different standpoints, be it electronics, packaging, photonics, keep going on an international scale. And basically, yeah, that's the takeaway message is Moodle is not cutting it anymore. You need another way to actually enhance the performance other than just to pack stuff, and HIR is the way forward. So, and maybe how much more time do I have, you think, Andrew? Can go down, please, again.
Yeah, you can keep going. You've got another 10, 15.
Okay. So slightly more closer to home, how can we get all these silicon in a package and electronic sort of heterogeneous integration approaches that have been ongoing, and how can we make them conducive to, how can we get them to talk to some of the slightly more nascent MEMS and photonics heterogeneous integration approaches that have also been going to? Because at the end of the day, we would like to develop things like system in a package that has the full functionality. The control electronics, we would like to have the storage like memory, but we'd like to have the sensors and photonics and MEMS, and we would like to have the very high bandwidth IO as well. If we can go down one. So what you will see from the photonics perspective is that photons are moving closer and closer to the transistor. So as the years went by, photons are no longer just carrying out the sort of longer communication, they're going closer and closer to data communication. The distances that they're making huge impact with are basically the sort of the 10 meters now, the 1 meter. And as the performance and form factor and bandwidth density improve, they're actually going to impact the multi-chip landscape as well. If we can go down one more. So what are the issues? So one of the biggest issues is basically the packaging. So we all know, working in photonics and electronics, that electronics is significantly more homogeneous than photonics. There is no one single platform, as I will show you down there, that actually cuts it for photonics. There are lots of things. The LEDs are made out of different sort of materials and platforms than PICs, than MEMS, than camera modules, than active cables, than sort of EO to OE, than WDMs. It's all very, very heterogeneous. How on earth do you actually package a lot of that? And you design this package. Go down one, please. So the toolbox for heterogeneous integration in multi-platform is quite challenging, right? So you're going to have board and package level. There is an interconnection level. Do you actually port the light out with antennas, or do you actually use optical wires like it has been developed in Germany? How do you put the passives and the actives together? What are the prospect of flexes? The sort of what type of interposer? There are some directions coming from packaging wanting lead-free, et cetera, et cetera. So lots and lots of challenging, particularly for photonics, much more so than electronics. So if you can go down one. So from a requirement, so this is from the push, so this is from these challenges. From the pull requirements, there's significant demand for us to be able to have standardized IOs. So we would like to have PCE sort of standards, for example, to allow us to get the Intel platform like EMIB that I showed you and others to actually have a very standard IO so they can design the chip itself, sort of the interposer itself, without having to worry about what every single one of these optical multi-chip modules or electronic multi-chip modules will do. So that's my personal dream, if you will, is for us to have standard IOs so we can so we are able to build independently the technology for the interposers independently from the technology of the actual chips that will go on it. So we can have standard interfaces. That's the only way we can move forward. So these are some of the directions that we aspire to pursue and to understand what your needs for on that front. Down some more. So sort of from a perspective of one of the biggest impacts where photonics could contribute to the heterogeneous integration is obviously the IO speed and density. So memory bandwidth and latency. One of the biggest challenges is getting the high bandwidth memory speed, which can be tens of terabits per second within the stack, to be exactly the same speed that this high bandwidth memory speaks to the GPU or a transistor. That's just severely limited now. So how can we do that? So these are some of the sort of, how does one improve the socket bandwidth of these interposers? One down. So what platform do we use for the optical solutions that we're gonna try to integrate in the system in a package? Do we use PICs based on sort of hybrid, or do we use indium phosphide, or do you use silicon? Silicon is great, but then it has some severe limitations in bandwidth density and power consumption if you take all things into account. Sort of usually some people who pursue silicon, not everybody is completely honest about accounting for all the components of where power is utilized. So if you can go down one more. So just to give you an example of a few of the challenges and the things that need significant heterogeneous integration to improve. So here are 2-3 examples. If we can scroll down one, the obvious one is basically the high bandwidth density datacom that I just spoke to you about. That's one. So being able to enable multi-chip module. So right now there is always grooming at the 25 by X and 56 by X using silicon photonics to get much beyond 100 gigabit per second. But will that work? If we keep going down, will that work beyond sort of 400G? Because for datacoms, you need well above 1 terabit per second. Switching and the bandwidth demand or the density of switching is getting larger and larger because of obvious sort of big data in data centers. So at this point in time, one of the biggest challenges of switching is the co-integration of the electronics and the photonics. Not because of, it's basically because of scalability. If you don't integrate them, the power consumption and the speed that are tenable to you are miserable. They don't make products that yield profit. Keep going down, at least from a scalability standpoint. 5G, so being able to remote stations, being able to handle the bandwidth, being able to actually switching devices in many ROADMs and muxes and demuxes, all that stuff for you to be able to handle the power consumption and the bandwidth needed for 5G, the heterogeneous integration of electronics and photonics is mandatory. It's not an option anymore, it's mandatory. Keep going down. So obviously from a sensing standpoint, electronics is great as far as CMOS, CCDs, but beyond that, we will need optofluidics, we will need microfluidics, to be able to do mini spectroscopy-based measurements on a silicon on a system in a package. All that will need some MEMS, and being able to integrate the MEMS is key. Going down, sort of some of the applications that are very cost-centric things are LiDAR. For LiDAR, it has to be in the hundreds of dollars, and without heterogeneous integration, that is just not feasible. Keep going down. So yeah, this is LiDAR. I think the last application that comes, I'm gonna skip because it relates to what my group does. And this is just a standard deck of slides that heterogeneous integration uses. So I don't want to describe what my group does, just it's a bit incestuous. Keep going down. Chip and wafer level, that's fine. Keep going down, thank you. Yeah, system and a package integration, ultimately speaking, will involve all these multiple layers stacked up and interconnected on interposer vertically and horizontally, so we can have 2.5 and 3D SiP integration. Go down. One of the challenges is optical test, for example. This is providing a huge headache for people who do design, because what sort of test vectors do you make to every single one of these chips when you test them independently, and then you go into heterogeneous integration? How do you test the entire assembly? It's a nightmare. Keep going down. These are the kind of challenges that we need to think about. Keep going down. Yeah. So some of the critical limitations in the integrated photonics one particularly is the co-design, basically the temperature, the packaging and the stress related to temperature uniformity and temperature drift, yeah, and that's it. We'll keep going down and down some more. So so there is like a highlight of a few of the emerging technologies that people end up finding as a potential solution for some of the challenges that I spoke to you about, be it plasmonics or be it sort of other nanoscale sources, but these are just an overview of things. Let's keep going. Quantum dot lasers that have extremely favorable characteristics to power up the optical side of these is one thing. We'll keep going down. That stuff related to my group for high bandwidth data rate, we'll leave that and keep going down, thank you. And that too, we'll omit that. And we'll get to the last slide, I think, where integrated photonics will be a key enabler in the sort of heterogeneous integration. It will provide us with key solutions that can help not just electronics, but many other of the system in a package technologies that relate to every field of our society, because it solves not just the data, but sensing and other attributes. And it provides us with a physical bandwidth density that is not paralleled by electronics. None of that could be realized right now with just increasing the number of chips or increasing the number of transistors or components. It has to be heterogeneously integrated from disparate, non-uniform, non-similar parts. Thank you so much for your time, and really sorry about the late start because of the hiccup.
Very good, thank you, Amr.
Okay, thanks very much. That's some really good context and views of how that integration methodology is used already in the technology we use. And in the next segment, I want to hand things over to Gordon Harling. He's the president and CEO of CMC Microsystems. And in his segment, he'll present some work underway on a new planar silicon multi-technology interposer platform. And the idea here is one specific solution that might fit within the wider roadmap of what Professor Halmi has just presented. So so I'll hand it over to you. Let me just switch over to these slides.
What? I thought you put it all in the new template.
Okay, you can all see this. 2.5 multi-technology silicon interposer.
Can you see that?
Oh, yes, I can see.
Okay, great.
Yes, yes.
Okay, next. You want me to take it? Okay, so we have, what should we say, a less ambitious program here. We actually did the work over the last couple of years, and the idea is that we create base wafers that are entirely covered with TSVs. So right now we're converting from 6 to 8 inch wafers. We pattern TSVs uniformly across the entire area. They're on a 500 micron spacing. There are no scribes, there's no free area, and so there's no real dedication to any one design or design format or shape, so that you're able to customize them. Whoops.
Just hit the forward button.
All right. Oh, okay, so we're crying out loud.
There you go. Go ahead.
Next. All right, thank you. So you can actually define any size or shape of interposer that you like. So this gives us a lot of flexibility, and we can inventory or stock these 8-inch wafers full of TSVs. We tried to make it such that we can ship these. So most of the folks in the university environment have 4-inch wafer capability. So our intent is that we will dice these like a pizza into 6 equal pieces, and they'll be able to fit within a 4-inch window. So you'll be able to do the RDL, the metallization layers anywhere in any of the 40 or so nanofabs. So you can pick one close to you and pattern it yourselves, or you can use our service. You provide us with the designs, and we will do the patterning, the component placement, and the final packaging. So this allows us to do a wide range of design sizes, to have a very short cycle time, because all that's custom is the RDL, not the TSVs, which take 3 or 4 weeks of processing time. And we can maintain an inventory. So we find that very exciting. All right. Now, in terms of packaging, obviously, if you want to have a standard package or a socket so that you can do non-destructive testing, we'll have to stick to a couple of standard sizes. So we've defined a 1 by 1 centimeter, a 1 by 2 centimeter, or a 2 by 2 centimeter as our standards. And we'll have sockets and packages for those. And that gives you a pretty wide range of capability, anywhere from 360 TSVs to 1400 on the same substrate. So, and the packages will be 3D printed in the early days. So we have a separate program which will allow you to 3D print a package and to cut and paste different functions. So you can bring in various types of SMA connectors for RF, or you can put in fiber optic bundles, or just simple electrical connections. So the packaging is running in parallel right now, but we do have some demo units that we can show you. And there's a meeting on Monday, I think, to discuss that program. It's a standard silicon interposer. The base wafer is 400 microns thick after etching. There are 2 RDLs on the top and 1 on the bottom. The bottom RDL is specifically configured so that you can put a ball grid array on the bottom of the device if you want to, so it can be mounted onto a PCB afterwards if necessary, or you can use the backside for components if you have a standalone operations or the system. It's flexible manufacturing, so there are a bunch of breakpoints where we can stop the processing and hand off to a different fab. So if you want specific things done, or if we come up with some standard formats, we'll be able to hand off either mirror wafers with TSVs, or wafers with just the RDL on top done, or wafers with just the bottom RDL. So very flexible, very modular, and hopefully people will be able to just do the steps that interest them. You may also want to do specialty coatings on top for ball grid array placement for tri-metal, or even sensors or heaters as well. Component placement, flip chip or wire bond, you can do either. You can stencil print onto it. We've got a variety of ways of getting that, getting the bumps in place, either on the interposer or on the chip itself. And there are a couple of use cases. One is if you're if you're an IP vendor and you want to demonstrate your IP, you don't need to combine it with every other product on the planet. You can put a processor and your IP down along with maybe interface components or Bluetooth, Wi-Fi kind of chips, and build it onto an interposer and make it look like a chip before your customer sees, it goes in and implements his own actual chip. So it's useful for IP vendors or people wanting to prove out their IP. And on the SoC side, if you're a small startup and you want to do a minimum viable product and demonstrate a small IC, here's a way to do it. So in terms of routing density, we're looking at 5 micron lines and spaces. We chose that as being easily doable in any of the MNT fabs across Canada. We could go tighter, obviously, but it would be harder for more people to pattern it. So we set the design rules at that level. But it's still, a PC board would be at best 3 mil lines and spaces. So we're 15 times denser in each direction in terms of routing density. So it still should be attractive. Rapid turnaround time, right? You can do early software development on your SoC prior to committing to a full fab. We actually, looked at a Polystem. This is Mohammed Sawan, his group. We're looking at doing a low-cost demo, and this is one of the feasibility proof of concept devices that we talked about. So you've got an avalanche detector, surface emitting laser, a HENT, and a core control chip in CMOS, all on the same substrate. So the other thing is you can put this into you can pump it down, you can put it into vacuum, and it won't outgas like a PCB would. And we're hoping that it'll have very wide temperature range. So that is something we intend to test in our current project. Here we are, line widths, just comparing PCB to interposer. The temperature range, spacing between layers, all interesting attributes of a silicon-based interposer. And we developed a PDK, so that is done in Tanner tools right now. We'll consider porting it to Cadence or down to PCB tools, depending on what customer demand is. But the design rules are available, and you can run DRCs on it. You can place standard components. And we have the most common surface mount and wafer level chip scale package footprints available, so you can pick and place. Again, the layers are all set out for you, and it's quite easy to submit a design or to migrate a PCB design. So we have a couple of reference designs. This one actually uses a printed antenna for Bluetooth. And the idea is it's a little device, it's got a battery on the back side. You can pick it up and shake it. The MEMS device recognizes the movement, and it measures temperature, the peak acceleration. It's got an ambient light sensor, and it sends that to an app on an iPhone, on an Android phone, I should say. So an interesting little demo, and it's available for anyone to grab it, both the layout and the software for both the app and the controller on board. So just one way that you could use this for IoT, for instance, and a design pre-done. So that's the BLE sensor node. You can grab the layout, you can grab the software, and you can run with that and integrate whatever other components you want. Well, there's we actually did a PCB version, so we can debug all the software, and I've got a demo of that in the office here. So the firmware is available and modifiable. And here was a project with McGill, with Odile, on a transimpedance amplifier and a photodiode where they needed very high speed. And so they actually mounted the two chips, and it was supposed to bond chip to chip in the air between the two, and just go to a high speed scope so you could see a photodiode to a transimpedance amplifier.
So what was the maximum speed of that, Gordon?
It was never tested. We actually had some problems. One problem is the TSVs. We tried to do silver-filled TSVs using a technology from a Californian company, and they turned out being in the K-ohms, around 7 K-ohms average, so it just wasn't usable. So now, we have a new project now that we're running. We're just trying to start up, and this project will be a 3-year interposer development program. Year 1, we're going to do polysilicon filled vias, but the polysilicon will be going through a number of parallel slits. So there'll be, just as before, it'll be a 100 micron diameter hole, but it'll be full of these trenches filled with polysilicon. So we're expecting to get under 10 ohms resistance. And in year 2 of the project, we will do a silicide. So we'll hopefully get under 1 ohm resistance. So for IoT, for stuff that's drawing a few milliamps, you won't even notice that kind of resistance. And year 3, in order to give it a real research sort of spin, we want to measure the cryogenic temperatures and see if it could be used to mount support circuitry for quantum qubits down at 4 degrees Kelvin or perhaps millikelvins. And right now we're supporting a project to do cryo testing on just the CMOS chips to see if they can survive being chilled and reheated. And we'll do some low power design stuff because obviously the chip can't generate any heat inside the cryostat. And then we'll be mounting those onto this future interposer and pushing it down. About 3 years from now is the intent. Yep, so that's the TIA. And then the Tanner Toolkit is fully featured. You can download it. I think it's accessible on our webpage now.
Yes, it is.
Yeah, so you can take a look at that. The only thing that will be changing is the confirmation of the TSVs, but all the RDL rules and stuff will still be the same. And we have a PCM, so that's what we test the process with. Is we have contact chains and 4-point probe measurements for the TSVs for all the metal layers individually, and we'll run that through the process first, and then once we've proven that the TSVs are good, we will we'll use the blank wafers for any customer designs that come up. So our intent is, if we can run the material through RDL at C2MI, we'll run it on 8-inch. We'll try and get 4 or 5 or 10 customers to share one 8-inch wafer. We'd keep our costs down. If you want to take some wafers yourself, we'll dice them up and we'll send wafers to you so that you can do them in your own lab if you're keen to do some wacky metallization, something that we don't do as a standard process. And eventually the intent is that this will become a standard process with regular runs that anyone can submit. And there's a 4-point probe test for sheet resistance. It looked pretty good, 32 milliohms per square for the TMAT1. And that's what the pattern, we're doing quarter wafers on 6-inch because that fits into a 4-inch window on most people's standard movement. So this was done at the 3IT, and this was the original run. Now, within the next 12 months, we'll have a polysilicon run, and we'll run the same PCMs and characterization on them. So it's not, what should we say, it's not bleeding edge, but it can incorporate multiple different kinds of devices. We should be able to get 2 gigahertz operation in the RDL. We can't really say much about the TSVs in terms of speed yet. They will be large and have lots of areas. There's bound to be a lot of capacitance there, and they will have a measurable resistance anywhere from 1 to 10 ohms. So that will limit the top speed of signals going through the TSV. So if you can stay on top, you'll do better than if you go through, send a high-speed signal through a TSV. But you should be able to use them for some power, not amps, but tens to maybe around hundreds of milliamps without appreciable loss.
Thank you very much, Gordon, for that presentation. In the next, the remaining minutes of this webinar, I'd like to engage all of you who are on the call now to discuss some of the questions shown on the screen now, to find out how we might engage with you to develop a solution for a problem that you're facing today. If you're interested in discussing with us, one great place to do that is this event coming up in 2 weeks in Edmonton called Nanovember. It's a series of 3 events across 3 days that are relevant to the topics we just discussed. So if you have a comment or question for any of the speakers regarding the presentations that you've just seen, I'll invite you to use the chat box in the Zoom control panel and just submit it there, and I'll take them and field them as we go along here.
Okay, can I just use the microphone to speak as well?
Oh, absolutely. Would that be Professor Kostowski?
Yes. Okay. This is Lucas Rostowski from University of British Columbia, Canada. Thank you very much for the wonderful presentation. I think integration of multi-chip modules is pretty key to move forward. So my work is primarily in silicon photonics, but increasingly we need lasers and amplifiers and other external chips and optical fiber attach, drivers. And so I completely buy into this, this notion of not trying to do monolithic everything in one single chip. The proposal for the transposer addresses the electrical needs, I think, quite well, except perhaps the high speed aspects. But can you say anything about photonic packaging and photonic co-integration? And I guess in particular, one of the areas I've been interested in the last maybe 5 years is I've been following the German work from Christian Kuss, looking at photonic wire bonds. And so I wonder if you can comment on whether that could satisfy some of the needs, or do you see any shortcomings with that approach?
Yeah. So let me take a stab at that first, and then perhaps Amr, you have something to add to that topic as well. CMC is engaging with Tyndall Institute, and I guess more broadly the PIXAP pilot line that has a portal at Tyndall Institute to provide a bit of a wider portfolio of photonics integration processes. So this would include initially a number of processes in the PIXAP supply chain in Europe, and then we want to expand that to offerings in Canada and elsewhere. So among those, I think with great potential is a photonic wire bond solution from using nanoscribe or similar technology, so multi-photon polymerization of a waveguide to provide chip I/O, right, of optical signals. So as far as I know, that's in experimental stages with the PIXAP portfolio. But what they're doing is demonstrating that the I/O, that the interface can be done with reference chips from specific PIC fabs. So I think they have HHI, IMEC, two types of IMEC, and Lyonics, and I think one other. And so we'd like to expand that to include AMF and a greater diversity of processes that come from Canada and even out from your way, Lucas. So that's our intent for the near future. Amr, would you have something to add?
I think from a perspective of the HIR itself, it's one of the options that are being put forth. However, it's very far away from being production worthy. But from practitioners like ourselves, including Lucas and ourselves, it's a capability that would be of great potential to explore if we have access to it, of course. It complements things like the work we're doing with Tyndall and such. It's complementary.
We're here to get you access to those things.
Thank you, sir. I know you're working tirelessly for that.
Thank you both for your answers.
Thank you. Okay, anyone else on the call with a comment or question, feel free to just unmute your microphone or send a message in the chat text box. So just while folks are thinking, if there's anyone on the call who thinks that you have a present need that could maybe demonstrate the silicon interposers platform that Gord presented, we would be very interested to hear from you and see how we could engage you in the development process of this upcoming run of polysilicon TSVs, so that we could spec the solution so it's ready for your application.
It would be amazing if we can get a feel for, if Gord mentioned the very tantalizing numbers, if we could actually confirm with some standard deviation the 10 ohms, that would make it, that would make one a lot more confident if one would come up and say, I'd like to use this. Because the worst thing I'd like to do is actually take some of that bandwidth and eventually it doesn't work because the speed doesn't match. So if we can just get some standard deviation that comes along with the 10 ohms resistance, because that will influence the speed, that would be great. Thank you, Gord and Andrew.
Yes, that's our primary preoccupation is the TSV resistance. So we'll see what that does. We did some ground signal ground probe plate pads on the BCM. In fact, there's an AC, a DC, and an RF BCM in that suite. So we should be able to reliably measure those things.
Great.
So it's the race now to get samples out. What's been holding us back is NSERC announced that not-for-profits could fund research programs, and I'm keen to use their money and use some leverage, so that I don't have to spend all of our cash on doing these R&D projects. But I haven't had an answer back from them as to whether we are really eligible, because we're 50% federally funded. Is that good enough, or would they consider that double dipping? So I'm trying to convince them that we're using money that does not come from the feds to do these projects. And I have a meeting with them in about 3 weeks' time, hopefully to advance that discussion. The other way is we'll just have to spend our money 100% and fund an academic research program to develop this. Slightly more painful. So the answer should come in a month, and if it's a no, then we'll go ahead and start this anyway, because I consider this important.
Any other questions, comments?
Yes, actually, I have a question regarding the interposer, this process. We're not actually targeting the high-speed stuff. We're actually targeting the high-power applications where it can be used medical treatment. So basically, we want to mount our power amplifier with the transducers together and sort of things, but with a high power. Is that possible, or this process is compatible with that applications?
If you can keep the power and routing on top of the interposer, then you can run fairly high powers. The problem is you won't want to pass an amp, say, through a 10 ohm TSV, because you're going to lose 10 volts of signal, and you'll be burning 10 watts, right, in your TSV.
Because I worry about those are the power loss become the heating and actually change characteristic of their circuits, then change entire things. Well, it's not easy to achieve the very high efficiency. So those will be the part of the power loss become the heat, and how this interposer can let the heat goes. And because there's a very condensed area, and those circuit will be mounted, or if there is a transducer, it's possible to integrate with this process will be great. But if not, it's mounted on the transducer. Is any way to let the heat go or something that's need a special technique?
Yeah, there's some interesting cooling ideas there in Amar's, Dr. Helmy's presentation. Those are all possibilities that we could sandwich coolers in with the interposer on the backside or that sort of thing. But silicon's a reasonable has a reasonable thermal dissipation, but not tens of watts. And these are small components too, so the heat density would be thermal.
Yeah, there's lots of innovations on that front coming from the electronics Gord. So reach out if solutions are if you're looking for alternatives.
Yeah.
Go ahead. And I wanted to comment that what you mentioned about NSERC is not strictly true, but we need to take this offline for me to suggest a few things for you. I just emailed Andrew privately. but we'll do that later. I don't want to take that.
I don't care what story
No.
we have to tell, as long as we get the multiplication.
No, I just I don't want to hog on the conversation, but there are certain things we need to discuss.
So just a clarifying question for, I think it was a caller, Mr. Joel, who asked about the medical application. So when you say high power, what kind of power are you talking?
Kind of, let's say 1 watt power, but we actually want to mount probably 100 transducers that can generate us enough mechanical power to do the medical treatment. So that's kind of an application scenario.
Okay, and are you thinking of 1 watt as in a power supply or the signal?
The power amplifier can drive the load. It's at least 1 watt. Sorry, yeah.
Right, I see.
For each of the transducer. It's also we're thinking that possible to integrate those transducers with the circuit, because that definitely can reduce the size. But I don't know how it works, because this transducer is kind of a mechanical thing. The acoustic wave will generate through the mechanical vibrations. Does those things vibration affect the circuit performance or not? Or
No, you're talking about piezoelectric devices?
yeah.
Yeah, no, so the vibrations won't affect the drive electronics.
Oh, okay.
Yeah, but I don't know what piezo materials you're using, but there's a potential there. And another thing we're doing is we're designing custom packages. So we have a project going forward where we'll be 3D printing metal packages, which could be great for thermal dissipation. So we can 3D print fins onto this package and try to bring the heat out.
So maybe I could suggest if you could reach out at either of the contact emails at the bottom of the screen there, we could exchange some more information, and I'd love to find out more about your application. Thank you very much. Any further question from the participants on the call? Okay, there's a question in the chat box here. What is the possibility of integrated thermal switches into a heterogeneous integration? Who wants to take that?
Thermal switch. Thermal switches.
Maybe I could ask the, this person to just clarify what is meant by a thermal switch. Is it like a thermally actuated
connection device?
Yeah, like a breaker or thermal.
I mean, if there is a bit more context, as Andrew is saying, if the gentleman or the young lady would tell us a bit more details, maybe we could point them in the right direction.
Okay. Yeah. So the thermal MEMS switches.
Yeah, for sure.
Yeah, there are standard procedures to that. It's just a matter of you want to integrate it with electronics or optics or fluidics, and there are ways to do that for sure.
I'm very keen to develop a library of MEMS devices that have been pre-characterized in a standard process. So right now, Microline, which is now part of Teledyne, has been developing process platforms for various types of MEMS devices like pressure sensors, thermal sensors, and that sort of thing. So we would like to get some MEMS designers in-house and actually build some standard components that people can use to de-risk their designs and use. And along with that, obviously, comes the electronic drivers and readout ICs for those. So if they're not available commercially off the shelf, I'd like to have CMC provide some standard designs that would do that.
Okay, we're coming to a few minutes after 4 o'clock. So if there are no further comments or questions, then please email us. We'd love to follow up with you after this call. I want to thank everyone for your participation in our community consultation. Your input is a big part of what makes everything turn around here, and we look forward to seeing you at various events around the country and continuing this discussion. All the best to all of you in your technology development. And that concludes this webinar.
Thanks so much. Greatly appreciated.